Hello, welcome to Advanced Composites. Today is the third day of the ongoing week, and what we plan to do today is discuss the number of elastic constants for orthotropic materials. So, we will discuss the case of orthotropy, and in particular we will discuss especially orthotropic materials. So, we are discussing especially orthotropic materials. So, what we have discussed is that if such a specially orthotropic material is subjected to extensional strains or extensional stresses, then it only generates extensional strains. And if we are subjecting the material only to shear stresses, then you only get shear strains. So, with this understanding, let us look at the stress strain relationship for an orthotropic material. So, on the left side we have sigma 11, 22, 33, tau 12, tau 23 and tau 31. And then we have this large elasticity matrix which is symmetric, because we discussed that in the last course, that a generally anisotropic material has 21 independent constants, and this is the symmetric elasticity matrix. And then we have the strain tensor. And what are the strain tensor strains? Epsilon 11, epsilon 22, epsilon 33, epsilon 12, epsilon 23, epsilon 31. Okay. So, these are strains and they are tensor strains, and we have already discussed what these tensor strains are. And let us look at these constants. So, this is 11, 11, 11, 22, 11, 33, 11, 12, 11, 23 and 11, 31. This is a symmetric matrix. So, this number is 1122, then the next one is 2222, 2233, 2212, 2223, 2231. The first element in this row is same as the second element in the first row, because we have said that this is a symmetric matrix. We will just write one more line and then you can fill up all the other good stuff. So, the third row will start from what? 1133, and the second element in this will be same as 2233, because this term will be same as this term because of symmetry, and this term will be same as this term because of symmetry. Okay. And then the third element in this is 33, 3312, 3323, 3331 and so on and so forth. So, you can fill up this entire column, this entire matrix in this way. Now, what we have said is that if this material is especially orthotropic, then if I subject it to extensional strain, only extensional strain, then it will only extensional stress, then it will only generate extensional strains. So, consider one case where I am having this material, and if I am subjecting it to only sigma 11, then it should not generate epsilon 1 2 which is a shear strain, epsilon 2 3 which is a shear strain, and epsilon 3 1 which is a shear strain, right, and vice versa, which means that these components should be 0 because they couple shear strains to extensional stresses. So, so this entire block, it goes away. This entire block goes away. Similarly, all this stuff also goes away, right. So, all these things go away. So, once they go away, then extensional strains will not produce shear strains, and shear stresses will not produce extensional strains, and vice versa. But there is one more condition which we did not explicitly talk about when we were discussing especially orthotropic materials, and we will discuss that now. So, consider a case so this is my 1 axis, 3 axis and 2 axis. Suppose I exert only tau 1 2 on this, right. So, ideally this top shear should be tau 2 1, but because tau 1 2 is equal to tau 2 1, I have just used the same indices. Okay. Now, if the fibers in this composite are aligned with the material axis, and let us say that material axis alignment is with respect to axis 1, then on this surface I will see only the ends of these fibers, and this material is being subjected to only the shear stress tau 1 2. Then first thing, because this is especially orthotropic, it will not have any extensional strains, but it will also not have gamma 2 3 and gamma 3 1, because when you look at the picture, it will only slide in the x direction, it will only shear in the x direction, it will not shear in the 3 direction or 2 direction, right. So, based on this physics, we say that tau 1 2 will generate only gamma 1 2, and then tau 2 3 will generate only gamma 2 3, and tau 3 1 will generate only gamma 3 1. Okay. So, what that means is that when I populate this matrix further, and 1 2 1 2, okay, I will call it 2 3 2 3, and the last, then I have 3 1 3 1. So, these terms, these two terms and this term, they couple tau 1 2 to epsilon 2 3 and epsilon 3 1, and similarly these terms will also. So, these terms which are there in the green blocks, they should also be 0, otherwise if I apply a shear stress tau 1 2, it will generate not only shear strain epsilon 1 2, but also shear strain epsilon 2 3 and epsilon 3 1, right. But we, because it is especially orthotropic, tau 1 2 will only has to generate gamma 1 2, tau 2 3 has to only generate gamma 2 3, and so on and so forth. So, all these elements in the blocks are also 0. So, once that is the case, then how many independent elastic constants we have? We have 1, 2, 3, 4, 5, because everything is symmetric, 6, 7, 8 and 9, 9 constants. Okay. So, these guys which are in purple boxes, they are all 0, all the elements in green boxes is 0, and the remaining elements are, because of symmetry, we have in this range, in this block we have 6 independent constants, and in this block we have 3 independent constants. So, total we have 9 independent elastic constants. An orthotropic, especially 3D orthotropic material, So, if a material is especially orthotropic in 3D and it is a 3D material, it is not like a thin plate. This has 9 independent elasticity constants. Okay. There is 9 independent elasticity constants. So, we will write that because we are now going to make a simplification. So, what is my stress tensor? Sigma 11, 22, 33, 12. So, what I will do is that while I am rewriting these constants, I will just rearrange the order of shear terms. So, instead of writing tau 12 first, I will write tau 23 first. It is just rearranging the equations, tau 31, and in the end I will write tau 12, because I want to get the nomenclature correct. Okay. And here I have my strain tensor, which is a 4th order, and that is multiplied by. So, this is the 4th order elasticity tensor, and this gets multiplied by epsilon 11, 22, 33, and then this is a strain 23, elasticity shear strain tensor 31 and shear strain tensor 12. So, remember here I am using epsilons even for shear strains. These are called strain tensor shear strains. So, epsilon 23 is tensor shear strain, epsilon 31 is tensor shear strain, epsilon 12 is tensor shear strain. And let us write down the definitions of these guys. So, epsilon 23 is del u3 over del x2 plus del u2 over del x3 times 1 by 2. There is a half factor, and similarly we can express relations for epsilon 31 and epsilon 12. Okay. So, these are the definitions of shear strains, but these are called tensorial shear strains because they are tensors. There is another thing called engineering shear strain, which is different, but for the moment this is our definition. This is what we are using in these equations. We are using tensorial shear strains, we are not using engineering shear strains. And what are the 4th order elasticity constants? E 11, 11, 11, 22, 11, 33, 0, 0, 0. So, like this. So, the second row is 11, 22, 22, 22, 22, 33, 0, 0, 0. I will write one more line 11, 33, 22, 33, 33, 33, 0, 0, 0. Then here we have all zeros. And then we have 4, 4, 4, 4. So, 4, 4, or you can actually, I will not call it 4, I will call it 2, 3, 2, 3. Then I have 3, 1, 3, 1 and 1, 2, 1, 2. Okay. And all other terms are 0. All other terms are 0. So, this is the stress strain relationship for a 3-dimensional, especially orthotropic material. Now, we will just rewrite these relations in engineering terms. Okay, in engineering terms. So, what we will do is we will call sigma 1 1. So, wherever we see 1 1 which comes as a group, okay, we call it 1. Wherever we get 2 2, we call it 2, not twice 2, but only once. Wherever we get 3 3, we call it 3. Wherever we get 2 3, we call it 4, and 3 1 is 4, and this is, so I am sorry, this is 5 and this is 6. Okay. So, my stress tensor becomes sigma 1, sigma 2, sigma 3. Actually, we will not use these 4, 5, 6 terms in the stress tensor, but we will use it elsewhere. And then we have tau 2 3, tau 3 1 and tau 1 2. Okay. Because we want to know what directions we are talking about. So, we will use these 1 2 3 terms in the elasticity matrix. Okay. But before we write the terms here in elasticity matrix, here we will write our strain tensor, but instead of strain tensor we will talk about engendering strains. So, epsilon 1 1 is epsilon 1, epsilon 2 2 is epsilon 2, epsilon 3 3 is epsilon 3, and then instead of writing these tensorial shear strains, we write engendering shear strains. So, what are engendering shear strains? Gamma 1 2 is del u 2 over del x 1 plus del u 1 over del x 2, and there is no factor of half. Similarly, gamma 2 3 we can have a definition, and gamma 3 1 we can have a definition. So, these, if we do not use this term half, then they are called engendering shear strains. Okay. So, what is the mathematical relationship between shear stress and engendering shear strains? So, for instance, I will give you an example. Sigma 1 2 is equal to, so we have seen this, sigma 1 2 is what? E 1 2 1 2 times epsilon 1 2 from this equation, right. This is tau 1 2 is equal to E 1 2 1 2 times epsilon 1 2. So, I am sorry, this should not be sigma. So, tau 1 2 is equal to E 1 2 1 2 times epsilon 1 2. But if I want to express the same relationship in terms of engendering strain, twice of this tensor strain is the engendering strain. So, this is E 1 2 1 2 divided by 2 into twice of epsilon 1 2, and twice of epsilon 1 2 is gamma 1 2. So, it is E 1 2 1 2 divided by 2 times gamma 1 2, and similarly we can write expressions for gamma 2 3 and gamma 3 1 also. Okay. Now, remember, engendering tensile strains epsilon 1, epsilon 2, epsilon 3, their definitions with epsilon 1 1, epsilon 2 2, epsilon 3 3 are same. The factor of 2 comes only for the shear components epsilon 2 3, epsilon 3 1 and epsilon 3 2. So, it is important to remember that. So, with that understanding, now once we are, so with that understanding we will rewrite this elasticity tensor, and in this elasticity tensor we will use the same convention which I talked about. So, wherever we see 1 1 we write 1, wherever we see 2 2 1 1 we again write 1, wherever we see 2 2 we write 2, wherever we see 3 3 we write 3, wherever we see 2 3 we write 4, wherever we see 3 1 we write 5, and wherever we see 1 2 we write 6. Okay. So, with that, so here we are going to write gamma 1, gamma 2 3, gamma 3 1 and gamma 1 2, and what are going to be our elasticity constants, and because we are abbreviating it and we are moving from tensor world to engendering world, we will not use this term letter E, but rather we will use a letter C. So, it is C 1 1. The first one designates 1 1, the second one designates again 1 1, right, because here we have 1 1 1 1. So, two 1 1s mean 1 1 and the second set of 1s means another 1. So, it is C 1 1, C 1 2, C 1 3, 0 0 0, C 2 2, C 2 3, C 3 3, C 4 4, C 5 5, C 6 6, okay. And all other terms in this matrix are 0, okay. All other terms are 0. And what are C 4 4? So, C 1 1 is same as E 1 1 1 1, C 1 2 is same as E 1 1 2 2 and so on and so forth. But these C 4 4, C 5 5 and C 6 6, they are different. So, C 4 4 equals E 2 3 2 3 times divided by 2. C 5 5 is equal to E 3 1 3 1, this is E 3 1 3 1 into 1 by 2, and C 6 6 is equal to E 1 2 1 2 into 1 by 2. Okay. So, now we have a relationship between engendering strains and stresses, and C are elasticity constants which couple engendering strains, not shear not tensor strains, engendering strains to stresses. So, this is the relation for fully orthotropic 3D material. So, the next thing we will do is we will talk about transverse isotropy. So, this is the case when in a particular plane the material properties are isotropic, but I guess the time for today's lecture is pretty much over. So, we will again continue this discussion tomorrow, and we will again consider the cases of transverse isotropy, isotropy, and the situation when there is plane stress case. So, with this we close our discussion for today, and we will meet tomorrow. Thank you.